So in this video, we're going to talk about the Nyquist-Shannon theorem. I'm going to link some videos below that talk about some of the lower level details, perhaps more in depth than I will. But in these videos, they do a couple different types of experiments. One just kind of showing you the waveforms approximated by uh, hand drawings, and another by showing you the actual analog output waveforms. And of course, that's probably what's most important. But I want to show a method here where you can essentially approximate that actual analog output waveform. And to do that, you essentially need to oversample your digitized waveform. The main difference between a digitized waveform and an analog waveform is, of course, that the digital waveform is a discrete representation of the analog waveform. And kind of wrapped up all in this is how you need to go about digitizing a waveform such that it can be perfectly reconstructed in the analog domain. And so also inherent in that is that the digitized waveform itself does not necessarily have to be a perfect representation of the analog waveform. It just needs to be something that stores data in such a way that that data can then be manipulated back to the original continuous waveform. And we're going to, again, oversample our digitized waveform to make it appear to be continuous. Of course, we can never really make a continuous waveform this way, but if we add a bunch of extra samples, then we are getting much closer to a continuous waveform. So I'm using a sampling frequency of 48 kilohertz, and the frequency that you're seeing on the screen here is 5 kilohertz. So there are 5 full cycles in a millisecond, and you can see the frequency representation at the bottom. Now, these videos will also talk about how a lot of our misunderstandings of digital waveforms and how they get recreated back as analog waveforms has to do with the way that we draw digital waveforms, but we don't really have a choice. We kind of have to draw them one of two ways. So here we have, well, that's not true. If we want to show a continuous waveform, we kind of only have two choices. And showing a digitized waveform as a continuous waveform is perhaps the flaw in and of itself that leads to the confusion. So each of these discontinuities is where the actual points are. And this representation is probably the more common one, to draw a straight line in between the points. Most correct would be to draw the points themselves only as dots or as stem plots, because it's only at those finite points in time that the waveform is actually defined. Everywhere in between, we don't really know. There was no sample taken at those points in between. So it's some amount of interpolation to kind of assume that the waveform looks something like, or would fall along this straight line in between. And of course, in reality, it doesn't. This was created with a actual sine wave, and we know that a sine wave is much smoother than this. It doesn't have all these discontinuities. So representing it this way with these straight lines in between the points has some amount of error. And we should also know that these discontinuities will create high frequency components. These things, these sharp changes in time would create high frequency components. They're very small in time, which just means they are fast in frequency, high in frequency. But we don't see that in our frequency plot. Well, why is that? That's just because the frequency plot only shows us the frequencies below Nyquist. So the harmonics that are generated, or the high frequency components that are generated by these discontinuities, are inherently out of band, and that's more or less the magic. So as long as we maintain this paradigm where everything is band limited, the discontinuities here are not actually going to cause a problem. And so the first thing I'm going to do to oversample my waveform is to make it look like a sample and hold. So for each of these discrete points here, I'm going to stack 9 more points that are all at the same value. And now it's going to start looking like this kind of stair step pattern, more accurately referred to as a sample and hold type of shape. So this is that sample and hold type shape. And now that I've increased my samples by a factor of 10, everything happens on the same time scale. So that means that the chunk of time has not gotten a factor of 10 longer. It means the sampling frequency has gotten a factor of 10 higher. And so now, before our Nyquist frequency was here at 24 kilohertz. Well, now it's up here at 240 kilohertz. And now we can see all these harmonic components that exist because of all these discontinuities. So again, each of these straight lines, this isn't just a plotting convention. This is because there are actually 10 discrete points at each of these values. And now that our sampling frequency is higher, our Nyquist frequency is higher, and we can see all these harmonic components. And it is true that some digital to analog converters operate by creating this type of waveform at an intermediate point. A simple digital to analog converter can be made by creating a sample and hold pattern. But to get back to where we started, all we have to do is filter out the harmonics that are created by these discontinuities. So the nature of sample and hold can be returned to the original continuous waveform without the harmonics by doing a low pass filter. Now, these are of course out of the range of human hearing anyway. But if I go and filter my sample and hold waveform, I now have something that is really smooth. I essentially have now a perfectly sinusoidal 5 kilohertz signal. This looks way better than the digital representation ever did. But again, this is still obviously digital. I'm just kind of approximating something in the analog domain. But this has 10 times as many samples as the original signal did. And that's because I'm pretending that it exists in the real world, in the voltage domain. And to pretend that it's continuous, I have to add a lot of extra samples to it. So I added all those samples, mimicked what the output of a sample and hold type DAC might look like, and then I low passed it, and lo and behold, the signal I get is essentially that of a pure tone. If I go back to where I started, again, you can see that these discontinuities here are created by the fact that I only have, 8 sample points per cycle? About 1, 2, 3, 4, 5, 6, 7, 8. Those discontinuities certainly create harmonics, but those harmonics are out of band. So as long as we have this reciprocity where there's an anti-aliasing filter at the beginning and there's a filter at the end that's akin to the anti-aliasing filter we had at the beginning, then the output in the continuous domain is interpolated in a way that's much better than this kind of linear interpolation that we see here. We have something that's more like a spline interpolation here.